Okay, we'll start now. We were discussing about the linear regression, right? So this is the problem, and we started discussing about the parametric approach. Parametric approach indicating that we had a model T equal to W transpose phi of x plus epsilon, right? So what is given to you is the data like one and the corresponding target, which is the noisy observations. We can say that x1, x2, x3 and so on up to xn. We have n set of observations, right? You have this input and the corresponding target, which is basically the noisy, right? And in this, epsilon is basically the random variable which is modeled as Gaussian with mean 0 and variance as 1 by beta, right? So that is the thing. How to get this W? Basically, y of x is W transpose phi of x, right? Using M basis function, like I can like W naught phi naught of x plus W1 phi 1 of x. It goes in that way, and you have this W subscript M minus phi subscript M minus 1 of x, right? So there are M basis function here, phi naught, phi 1 and so on up to this M minus 1. There are M basis function, and in general or in practice, this is this basis function phi naught of x is chosen as 1. So all those things we already know, right? Our requirement is to estimate this W given data. In connection with this estimation for this W, to estimate W in connection with that, we have three density functions, probability density functions associated with that. One is the prior W, is a prior density function, and then we have what is called the W given, and because of this observation T1, T2 and up to this Tn, and of course this corresponding input x1, x2 and so on up to this xn. This is more general, we can write like this. This is what we call this posterior density function. So posterior density function, if I know this posterior density function, we can actually for conditional median right conditional mode. So these are all the solution for estimating this W. This one hereafter, like f of W given T, x is anyhow it is going to be there. We say that it is a posterior density function. Is a posterior density function. What is called this likelihood function f of T given W. This is likelihood function. Which we can using this base f of T given W is as f of w into f of whole divided by f of w. So this is the thing. In fact, we can write the other way around also. F of w given t f of t given w, f of w whole divided by f of t in this way also. We are considering this conditional mode, means maximizing the posterior density function, which is otherwise called map. If I consider trying to maximize the posterior density function, so maximizing this left one is equivalently maximizing the right hand side, and then this denominator is not having any w, so this is not playing any role as far as this w is considered. And you are assuming, this is a very important assumption, that f of w is assumed as constant. It means that it is uniform distributed. Uniform distributed, it is chosen as constant. Under that circumstances, maximizing this likelihood, that is f w given t, right? If I, instead of maximizing this, we can actually go for maximizing this f of t given w. Both are equivalent, right? So that is what we call it as maximum likelihood estimation. F of t given w is not simple, because t is modeled as epsilon, right? Here this t, of course, t1, t2, so let us say t1, it is y of x1 epsilon. Actually, this epsilon is actually making this t1 as random variable. Y of one is constant, so it means that t1 follows, t1 also follows Gaussian distributed. The variance is the same, but mean is getting y of x1. So that is the thing, right? Because your epsilon is Gaussian distributed, right? It means 0 and variance is 1 by beta, and hence this is what is happening, right? So we understood that maximizing this likelihood function, which we discussed in the previous class, is ending up with solving phi w equal to t. That is what we got. So this is basically what we call it as least square setup. Least square setup. In fact, maximum likelihood ends up with least when the noise epsilon is Gaussian distributed. Solution and maximum likelihood both are going to be when the noise is Gaussian. But you can even attempt solving this one directly, right? In that case, it is not maximum likelihood estimation, it is what we call it as least square estimation, right? So we can actually split this problem as two solutions, right? One is least square solution, another one is this maximum likelihood solution. Least square solution and maximum likelihood, right? Least square solution and maximum likelihood solution. But both are going to be the same when the noise is Gaussian. Otherwise, both are going to be different. So that, right? And we understand that this solution W that is obtained as using the pseudo inverse phi transpose phi, the whole inverse phi transpose t. So this is what estimate for this W, right? That is fine. But the only problem in this case is it is more data dependent, right? So it depends upon what training data you are giving, and you get different estimate for W, right? You get different curves for different data set. So it ends up with what is called overfitting. Overfitting, it tries to fit all the training points. It tries to fit all the training points, and hence it is what we call it as overfitting. To avoid that, we purposefully give some right disturbance in estimating this, this W estimate by the parameter called lambda, which is called regularization constant. This is a regularization constant. We try to right estimate as W cap as what? Phi transpose phi plus lambda I, the whole inverse. Understand that one way of viewing this lambda as what? The regularization constant. And this can also be viewed as the constraint, right? Lagrange of what is called constrained optimization, right? We can as the regularization constant blindly, right? The state way. We can even view this one as a right. In case of this constrained optimization problem, lambda is treated as Lagrange multiplier. What does it mean? It means that every function which you are trying to minimize doesn't have only one term that minimizes this error, right? It also tries to minimize the magnitude of this W, right? So, this objective function which we discussed in the previous class, right? So, we can, in that context, this lambda is viewed as the Lagrange multiplier. Today, this we already discussed. I just wanted to recollect we discussed so far. Today, what we are going to extend this concept to this Bayes optimization, right? Optimizing W, right? Right? W using this Bayes concept. The idea is very simple. We wanted this f of W, right? So that is what we need. If I know that, then we can directly go for conditional mean and median and MAM and more. So, but to get this, what is restricted to you is T given W, f of W have W, right? Likelihood, we made this f of W as constant, that we did. But now what we are going to do is, f of W is also Gaussian. Gaussian. That is the very important thing today. What you are going to, right? Is that all right? Right? See, this f of W is also assumed as Gaussian, right? So means the W like to estimate, right? So that is also modeled as Gaussian, right? So in that case, we can actually find out what is the density function of given, because we have a direct relationship, right? Using the relationship, we can actually find what is f of w given t. In fact, it is observed that this f of w given t is also happen to be Gaussian. See the concept. Let me repeat once again. Estimation, we assume that f of w is what? Constant, right? This is maximum likelihood case. Right? Now we are going to use this f of w as, right, function. It is also partially distributed. So that is the interesting point, right? So what happens if I do that? If I w, but f of w given t, this also follows this Gaussian distributed. That is what we are going to discuss now. Right. So now let me have a quick overview of what we discussed, and then we'll go for this Bayes technique. Right. So what is here? The slide that gives you the idea about that. So recap. T is the observation, noisy observation. This is the model, right? Parametric model. T is a scale vector x. Right? H1 is Gaussian distributed by beta, which is unknown. So given the training data, establishing the relationship, right? So this is what actually requirement, right? Establishing the relationship y of x is equal to w transpose y of x needs estimating this w, right? So f of w given t is the posterior, f of t given w is the likelihood function, and f of t given w, right? So f of t given w I have written here. Let me change this as f of, in this is a mistake. This is incorrect. This is f of w, that can be written as f of divided by f of, and what is more important is we are going to model this w. Let's see one by one in that. F of t given w distributed, that is known because you are plus epsilon, so t is Gaussian distributed. Getting shifted, variance is 1 by beta. This also we discussed. So in like the that is equal to f of t given w into f of w whole divided by what? F of t, right? So in case of likelihood estimation, f of w is assumed as what? Uniform. So maximizing this is say that, and the denominator is not playing a role in it. This is the maximum likelihood estimation, right? So and that of t given w is same as that of maximizing the logarithm of the likelihood function, and hence ends up with the setup phi w equal to t, and that ends up with the, right? So now this is the important point. What if w is assumed as what? Multivariate Gaussian density function, right? Whatever I'm going to tell now is very important. Once again, I will write that f of w given t, that is equal to f of t w into f of w whole divided by f of t, and you already know f of t given w is model as Gaussian. This is known, right? But this also I'm going to now model as Gaussian. That is the thing. This is also going to be modeled. So that is the difference now. This is already model as at what is happening. W is a density function and covariance matrix not, right? So because yeah, W is basically vector, right? W1, W2 will have multiple elements, but right. So in fact, to be more precise, it starts with W0 and ends up with what? W-1. There are M elements in it. It's a vector. So each element is Gaussian distributed. Each element is Gaussian distributed, and all W2 and up to this W-1. That follows actually moderate Gaussian density function, right?
Hello? Hello?
Sir, you are not audible.
Hello. Hello. Vishnu, was he good?